Welcome to The Explainer. Okay, let's dive right into the incredibly fascinating world of visual translation. Today we're exploring this really fundamental concept that somehow bridges mathematics, art, science, and engineering, and we're doing it all through the focused lens of drawing cross-sections. Think about this for a sec. How do you actually capture a massive three-dimensional world on a flat, two-dimensional piece of paper? Well, this simple question is literally the core problem across almost every spatial discipline out there. And the answer, more often than not, lies in one absolutely powerful tool, the cross-section. It is, hands down, the ultimate way to reveal what's hiding right beneath the surface.
So to unpack this, we're going to view it through 5 different lenses of scale. We've got 1, the geometry of slicing, 2, precision in biological drawings, 3, creating form with art, 4, mapping mountains and geology, and finally, number 5, engineering the built environment.
Part 1. The geometry of slicing, the conceptual foundation.
Let's start with the absolute basics, right? To really understand the complex stuff later on, we need to ground this abstract math in something we all know and love: slicing food. So imagine you're holding a knife, getting ready to cut right through this exact wedge of cheese. In mathematics, this action is described by the plane intersection postulate. Basically, it tells us that when a plane, which is your knife, intersects a solid body, the cheese, the resulting two-dimensional shape formed right there at that intersection, that is our cross-section.
I know, the formal definition sounds kind of dense, but the practical reality is pure magic. The shape of the cross-section changes entirely depending on the angle of your cut. I mean, slicing that same block of cheese could give you a square, a triangle, a rectangle, or even a trapezoid, just based on how you orient the plane. You're literally discovering 2D shapes hiding inside a 3D object.
Math textbooks lay out a super clear progression for drawing these theoretical cross-sections. You visualize a horizontal plane, draw parallel line segments where the plane hits the lateral faces of the object, and finally shade the cross-section so it really pops out visually. It's clean, it's logical, and it's perfect. But as we scale up into the messy real world, the rules for drawing these sections begin to change completely.
Which brings us to part 2, precision in biological drawings, the observational middle.
Okay, let's step into the laboratory. Here, we step totally away from mathematical theory and deal with living things. Drawing cross-sections of tissues and cells under a microscope requires uncompromising, objective accuracy. In biology, drawing is a strict form of scientific communication. You are solely recording qualitative observations. That means you draw exactly what is seen, not what you think should be there. You use a razor-sharp pencil on unlined paper, creating continuous, crisp lines. And the most crucial rule of all? Absolutely no shading allowed. None. You outline only the distribution of cells, leaving out all idealized coloring or texture. It is clinically objective.
Part 3. Creating form with art, feeling the surface. Now, this is where things get really cool. If we take that exact same pencil and hand it to an artist, the rules for drawing cross-sections completely flip. We go from extreme clinical objectivity to sensory illusion. This brilliantly illustrates how differing goals totally dictate our approach. Biology demands flat, unadorned outlines to record data, right? Art, on the other hand, uses something called cross-contours. Artists use these cross-contours, alongside varying tonal values, specifically to trick your eye into seeing three-dimensional space on a flat piece of paper. It's a completely different philosophy. Cross-contour drawing actually teaches your mind to sort of feel the curved planes of a shape. Instead of just tracing a flat silhouette, you use curved lines and varying tonal values, lighter in the highlights, darker in the shadows, to gradually, deliberately build a realistic rendering. The more curved the line, the rounder the form feels to the viewer. It's how artists literally breathe life into a 2D page. Part 4. Mapping mountains and geology, the macro application.
Let's zoom way out to the macro scale and see how Earth scientists use these exact same cross-sectional principles to slice through entire landscapes and mountain ranges. Geologists use what are called topographic profiles. If you've ever looked at a map with all those squiggly contour lines, you know it can be super hard to actually visualize the terrain. Well, by drawing a line across that map and projecting the elevations downward, they generate a visual side view of the landscape. It helps them fundamentally understand what those flat map lines actually mean for real-world hills and valleys.
The process is pretty systematic. You draw a horizontal line matching your map slice, plot the elevations based on the map's contour intervals, and then connect the dots. But the absolutely crucial thing to remember here is that nature isn't a series of flat, jagged stairs. When you're connecting those dots, it's gotta be a smooth curve. Hilltops naturally go smoothly above the highest contour lines, and valleys dip just below the lowest ones. Now here is a wildly fascinating trick geologists use. Often, a real-world cross-section of a massive landscape just looks completely flat on paper. So they use something called vertical exaggeration. They will vastly exaggerate the vertical scale, sometimes stretching it 50 times its normal height. Because of this, subtle, hidden geological variations suddenly pop out and become highly visible. It's a deliberate distortion to reveal the truth.
Part 5. Engineering the built environment, constructing reality.
Finally, let's look at the folks who take all these concepts and use them to physically reshape our world. Civil engineers use these exact same cross-sectional tools to alter the Earth and build our modern infrastructure. In engineering, a cross-section isn't just a picture, it's literally an instruction manual. By reading the elevation and gradients in a longitudinal section and comparing the existing ground to the newly designed elevation, engineers calculate whether they need to cut Earth away or fill Earth in. This single slice calculates the exact transport of dirt, where massive machines need to go, and the sequence of the entire construction project.
The crucial point here is captured perfectly in this quote. A cross-section shows you the results of a slice, but, it's not the whole story. Overlaying that vertical section with the top-down plan view is what actually reveals the constraints, the design intent, and the full reality in 3 dimensions. You absolutely have to correlate the two to truly see the project.
So we've gone from slicing cheese to slicing mountain ranges, but the underlying truth is exactly the same. The 2D cross-section is our ultimate key to unlocking a 3D world. The next time you look at a building, a landscape, a piece of fruit, or even just the room you're sitting in right now, try to visualize the incredible, unseen geometry hiding just beneath the surface, waiting for a plane to reveal its secrets. Thanks for joining me on this explainer, and keep looking deeper.